Section 6.4, we'll talk about a very important theorem that we're going to be using called the central limit theorem. Now, we're not going to go into the theory of how this theorem was derived or what the proof of it is. We're going to talk through it, and by far what's going to be most important for us is the examples that follow with it. So even if this theorem seems kind of abstract from the start, once you see some examples and you start to get a feel for how it's used, it's not as intimidating as it might seem from the start. So what the central limit theorem says is, suppose that we have a random variable that has a distribution with a mean of mu and a standard deviation of sigma. Now, it's important to note that there's a phrase in there which says that the random variable may or may not be normal. Now, for continuous distributions, the normal distribution is all we have looked at so far in Chapter 6. So what do we do in the case when the population is not normally distributed? Well, the central limit theorem gives us a tool to use in a case like that. So we're continuing along with the assumptions. We're told to suppose that a sample random samples, all of the same size, are selected from the population in such a way that all possible samples of size n had an equal chance of being selected. Now, that is actually the definition of what a simple random sample is. So that line is sort of redundant. We're just saying that if I pull multiple samples from a population, that all the samples have the same size, and any given sample that I choose had an equal likelihood as all the rest of the samples of being the one that was actually chosen. Once we have those in place, there are three conclusions we can draw from this. The first one is that the distribution of sample means, and that should be plural right there, so the conclusions that we can draw is that the distribution of the sample means, and the notation that we are going to use from that. The sample means, remember the notation that we have been using for sample means is just going to be x bar, will, as the sample size increase, approach the normal distribution. The second one is that the mean of all sample means is the same as the population mean mu. Now, the notation for the mean of sample means is going to be mu with a subscript of x bar. Now, I'll explain what this means in this space below in just a moment. But the last conclusion that we can draw is that the standard deviation of the sample means, which is going to be denoted by sigma sub x bar. Whoops. There we go. This is the way we find this standard deviation is we take the standard deviation of the population that we know from the problem that was given to us. And then we're going to divide this by the square root of the sample size. And once you divide this by the square root, you're going to end up with a number that's smaller than sigma. So the standard, the sample means are going to have smaller smaller variation than the original data values themselves. So before we work an example, let's talk about what I mean by when I say mean of sample means. Suppose I have 3 samples. So here's there's sample 1, Here is sample 2. And here is sample 3. Now let's assume that for making the ease of calculation, let's assume that these samples have 3, the sample size is 3 in these cases. So this sample is going to have x sub 1, x sub 2, and x sub 3. This sample is going to have x sub 4, x sub 5, and x sub 6. And this sample is going to have x sub 7, x sub 8, and x sub 9. Now, in practice, well, in theory, what's happening is we're not drawing 3 samples. We're drawing many, many, many hundreds, thousands of samples, a very, very large number of samples. Here, I'm keeping things small so we can get our head wrapped around what's happening. Now, if I give you a sample with 3 elements in it, and I ask you to calculate what is x bar. Now, we know how to calculate an average. So what I'm going to do is I'm going to denote this average, this mean right here, by x bar sub 1, because it is my sample mean for sample 1. And we know how to find that. This is just x sub 1 plus x sub 2 plus x sub 3. And then we all divide that by 3. And if I keep going, we're going to get exactly the same thing for x sub 4. I'm sorry, for sample 2 and sample 3. So it's going to look like this. Divided by 3. And x sub 3 bar is x sub 7 plus x sub 8 plus x sub 9 divided by 3. So far, nothing new. We've been doing this since section 3.1. So, but now what if I asked you this? You see these 3 numbers right here? This one, and this one? What if I asked you, take these 3 numbers that you just calculated and find the average of those numbers? Now, these are means because they're averages. That's how we evaluated them. We took an average of these data values. But if I average these means, the result is going to be what we're calling mu of x bar. And this is going to be x sub 1 bar plus x sub 2 bar plus x sub 3 bar. Divided by, well, there were 3 means here, so I would divide by 3. And if you were to simplify this, you would see that mu of x bar is actually just the same thing as mu, because you would get it by just averaging all of the data values together in one big group rather than just breaking them up into 3 separate samples. So this mu of x bar, this is, if I have all of these sample means that I'm calculating for all of the large number of samples that I have collected, then the average of those sample means is going to be a mean of means, and it's going to get this notation. But this right here, this is the main thing you need to remember, that the mean of the sample means is just the same as the mean of the population you started with. Now, that seems like a long-winded way of saying just use the mean that you start with in the problem, but this is why we can say that is true. Now, what we're not going to do is we're not going to prove where this number right here came from. So what I'm going to do right now is I'm going to pause the video just a moment to clear out this area because we really don't need it anymore. The most important thing we need comes from these last 2 statements right here, which says that this one says that mu of x bar is equal to mu. And we have the other formula for the standard deviation of sample means right here. So give me just a moment and let me clear up some space. So before we look at an example, let's look at some commonly used rules that we're going to be using for the central limit theorem. Now, remember at the start that right up here, it says that the random variable does not need to have a normal distribution, but that its sample means will as the sample size increases. In order for our approximation to be good enough, if the population is not normally distributed, then we're putting a minimum value. We need to have sample sizes bigger than 30. If it's smaller than 30, what's going to happen is if you try to estimate a non-normally distributed set with a normal distribution, there's going to be an error in there. But what this rule says is if your sample size is big enough, then the error that you get is going to be offset by the ease in calculation that you obtain by being able to use a normal distribution on that problem. So that's all we've got to remember. And we'll know from the problem will tell us if it's normally distributed. And if it's not, we're going to check the sample size and just make sure it's bigger than 30. But if the original population is normally distributed, the sample size doesn't matter. The distribution of sample means will be normally distributed. So this next problem is going to have two parts to it. So let's read the problem first. We're told that IQ scores are normally distributed with a mean score of 100 and a standard deviation of 15. So let's focus on part A first. It says if one person is selected at random, find the probability of that person having an IQ score over 133. Now, hint, we have already worked this kind of problem already. Part A is a 6.2 problem where one person is being selected from your population and you're given the population's mean and the population's standard deviation. So if we were to look at this, here is our bell curve. These are going to be messy, get used to it. So if one person is selected at random, what's the probability that the IQ score is over 133? So here's the mean right here in the middle. So the mean is 100. This horizontal axis represents random variable values, represents individual IQ scores. Now, we're trying to find that the IQ score is over 133. Now, 133 is way over here. And I want to find the probability that I randomly select one that falls in this region because it said greater than 133. So this is just going to come down to, well, before I say it, let me ask you a question and then think about it before I give you the answer. We're trying to find a probability from a known random variable value. Is this going to use normal CDF or inverse norm? Pause for a moment if you need to think about it. Given the fact that we are trying to find an area, then this is going to be a normal CDF problem. So I would go to my calculator. I would put in normal CDF. The mean is, the lower bound of this region is 133. The upper bound is, I'm going to throw a really big number in here. The mean is 100. The standard deviation is 15. And this is going to give me a value that if I round it to a couple decimal places is going to be 0.0139. So this is about 1.39%. So a very low probability that a randomly selected person is going to have an IQ greater than 133 if that mean and the standard deviation are correct. So part A should look familiar to you. we were doing it in 6.2. This is the lecture that we were doing on the last day before the break that we had. Now, look at the difference between the wording of Part A and Part B. In Part A, one person was being selected. We wanted to find the probability that that one score hit a certain region. Now, we're taking a sample of 9 people. And we want to find the probability that if I average all of their IQs together, that their IQs hit a value that's larger than 133. So this picture arguably is going to look very similar. So let me undo that. I can do this a little better. So at least I can draw a straight line. And here's my bell curve. So these two pictures are going to look similar, but there is a difference. The mean, remember, go back to the previous screen if you need to. The mean that we use for these sampled distributions is exactly the same as the mean of the population those samples came from. So I get to use 100 as my mean for this as well. But over here, this was sigma right here. We're not going to use 15 as our standard deviation. So the main difference between these two pictures is that this horizontal axis is not random variable values. These are not IQ scores. These are averages of IQ scores on this horizontal axis. And that may seem like a minor change, but it's what's allowing us to use the central limit theorem. So here's 133, and we're trying to hit the same target, but it's going to be a little harder to get in this region now, because over here I just needed one person to hit the region. If I want an average of 9 people to fall in this area, I need several of those individuals to be in that area themselves. For example, if all 9 values are down on this end, there's no way they can average to 133. So all we're going to do is, a lot of this is going to stay the same. It's still normal CDF because we are still trying to find a probability. The lower bound is still 133. The upper bound is still a really big number because it includes this tail. So I'm just going to throw a really big value in there. The mean, mu, I get to use the same value. So I'm going to put 100. Now for the standard deviation, remember that sigma of x bar is equal to sigma divided by square root of n. Now, so I'm going to type in 15 divided by square root of 9. Now, I know that 9 is a perfect square in this case, and 15 divided by 3 is 5, so you could just put 5 right here instead of this whole expression. But if this would have been like 5 divided by the square root of 11, then you would have to, if you tried to put that into your calculator, you're going to get a decimal. So the normal CDF function will allow you to put an expression like this. And all you have to do is take the original. Notice that it's just adding a few characters at the end of the standard deviation right here. So part A was a 6.2 problem because it was one person being selected. Now, part B is the new material for 6.4. We're trying to find the probability that a sample mean hits a certain target. That's the difference between 6.2 and 6.4. So you'll notice that when you work through the homework on my math lab for section 6.4, a lot of the problems have a part A, which is 6.2 work? And then they'll modify the statement into a problem regarding sample means, and you can see that the work that I did to calculate this, and by the way, this value right here, I didn't write it down, but this, if in my calculator, I come out to 2.0665 times 10 to the negative 11th. That means that there is a decimal point followed by 10 zeros before the 2 starts. Look how small this number is. It's practically 0. So here we had about a 1.4% chance of one person hitting this target, but practically 0% chance that a group of 9 people will have their average hit that same target. Okay, let's talk about the rare event rule for inferential statistics. Now, we have talked about this in chapter 4 before, but it's coming back again now. And what the rare event rule says is, if under a given assumption, the probability of an observed event is exceptionally small, then we conclude that our assumption was probably not correct. So the example that we're going to use to demonstrate this is this problem involving SAT scores. So what we're told in the problem is that SAT scores are normally distributed with a mean of 1518 and a standard deviation of 325. 16 people are taking a review course to help them improve their scores. But we're going to assume that the course did not affect their scores. So we have to make an assumption. We can't say from the start that the course did help them significantly. Just because you take a course doesn't mean it improved your score. What if I announce that I'm going to give everybody a review for the final, and then when you come in for the review for the final, all we do is sit and blow bubbles the whole time? Well, that did not help your score at all, but I called it a review. So what we're going to do is just make the safe assumption that that the course had no improvement, and see if we can be proved wrong. So we're going to start by looking at part A that says, if one score is randomly selected, find the probability that it is greater than 1800. So draw your little picture. Here's your bell curve. I'm going to put the mean right in the middle, which was 1518. And greater than 1800. So 1800 is way over here. Greater than 1800 is this region right here. Notice that this is just like the last problem. So my answer to this would just be normal CDF. The lower bound is 1800. The upper bound is not set, so I'm going to throw a really big number in there because it includes the tail. My mean is 1518. 1518. And my standard deviation is 325. Put that into the calculator and see what you get. I get 0.1928. So this is about 19%. So about 1 in 5 people will, if you just randomly select one person, about 1 in 5 will have a score that's 1800 or greater than 1800. Now, this horizontal axis represents SAT scores. For part B, this says if we were to randomly choose, so of all the people that took SAT scores during this time period, we're going to randomly choose a group of 16. Now, I'm going to mention that this group of 16 right here is not the same 16 that took the course. This is a random selection from the population. What we're testing to see is if we were just to randomly get 16 people together, what is the probability that the average score of those 16 students is greater than 1800? Well, this is just like part B of the last problem we did. The picture looks the same. It's still going to have 15, 18 here in the middle. It's still going to have a bell curve because we're using the central limit theorem, which means we can approximate with a normal distribution. The horizontal axis represents sample averages now, and we're trying to find the probability that that average is greater than 1800. So the pictures look very similar, but what the horizontal axis represents is different. Okay, so since it is a group of 16, and I'm trying to find that the probability that their mean score is greater than 1800, then this is where the central limit theorem comes in, and I'm going to put in normal CDF, normal CDF. I'm still going to use 1800. I'm still going to use 9999999. I'm still going to use 1518, but I'm going to take this standard deviation, that 325, and I am going to divide it by the square root of my sample size. So 325 divided by the square root of 16. And this comes out to 2.595 times 10 to the negative fourth. So 0.000255. Now, our threshold by what we're calling exceptionally small right here, we're going to use less than 5% or less than 0.05. Okay? This number is much less than 0.05. So what the rare event rule says is the probability that we just happen to get 16 people by chance that had their score greater than 1800, the probability of that happening by chance is so small that if these 16 people who take the SAT review course do have a mean greater than 1800, that means it probably didn't happen by chance, that some outside influence affected their score, which means that review course helped them. So is it true that the course had no effect on their score? No. Because the probability of this occurring by chance please excuse my handwriting. This occurring by chance is less than 0.05. That's all we were looking for. This number is less than 0.05, so this was unlikely to have occurred by chance, which means that the assumption that we made was probably not correct, so that it probably did affect their score. Now notice I skipped over part C. Now, part C says, why can the central limit theorem be used in part B, even though the sample size does not exceed 30? Before I answer this, pause the video and see if you know the answer for this before I give the answer. Remember what the central limit theorem, what the commonly used rules for this was. It said that if the population, that you only need the sample size bigger than 30 when the population is not normally distributed. If the population is normally distributed, which it is in this problem, then any sample size can be used. Now, I will tell you that for all of the problems that we are going to be doing, you're going to be able to apply the central limit theorem. I'm not going to give you a problem where the population is not normally distributed, but I give you samples of size 25, for instance. If the population is not normally distributed, your samples need to be big enough, and 25 just isn't. But if you do have if your populations are normally distributed, which in many cases your populations are, but they don't have to be, then that's when you could the sample size doesn't matter anymore. So if you start out with normal distribution, use any sample size that you've got. If it is not normally distributed, you need sample sizes of that exceed 30. Now, we're not going to get much more in depth with details regarding sampling distributions, because notice we skipped from section 6.2 to 6.4. Sampling distributions are covered in detail in section 6.3. So we're not going to delve into it in any greater depth than what we already have. So the homework for section 6.4 is going to be very similar to the two problems that I've just worked out for you now. And there are other worked examples in your book. I know many of you probably have never cracked your book. If you do not have a physical copy of the book, there is an electronic version available in the resources on my math lab. If you're not sure where, ask me and I'll help you find it. And if you're going through the homework and you got a question to ask, you can always send me an email and ask me, or bring it to the Zoom meetings that I have during my office hours. And that'll give me an opportunity to work that problem out for you. In the meantime, reach out to me if you have any trouble, and good luck.